The fundamental theorem of calculus relates the differentiation and integration. So just to remind ourselves, differentiation we're talking about derivatives, and we're talking about the slope of the tangent line to a function at any point. And just recently we were talking about integrals, and specifically definite integrals. So we have something that looks like this. Okay. This is essentially the adding together of an infinite number of areas, rectangles, that we calculate the area using the function, the values of a function. The area depends upon whether the function is above the x-axis or below, whether it's a positive or negative. But this is fundamentally what it is. And so we're going to relate the derivatives with these integrals. And the first part of it, I'm just going to cover very briefly. And I'm going to say that derivatives are the inverse operations to integrals. Just like if you have, for example, x squared, the inverse of the x squared function is the square root function. And we end up with, assuming that x is positive, we end up with just x. And the other way around, it also says that if we have the square root of x and we square that, that also leaves us with just the x. And so similarly, we have an inverse relationship between derivatives and integrals. And this is how we are going to write that. If we have an integral from a to x, so instead of from a to b, two specific numbers, it's from a constant, but it goes to any value of x of a function. And here, because we're using x here, we're going to use what we call a dummy function, or a dummy variable here, a t. Normally we would write f of x dx, but we're going from a to x here, so we don't want to have x plugging into x. But if we have a function like this, it's a definite integral, and we take the derivative with respect to x of this function, we end up with simply f of x, the function here with the x plugged into it. And there's let me give you an example of this. So for example, we have a function -3 to x of the square root of the tangent of t dt. And we take the derivative with respect to x. We're going to get the function in here. So this is the function here. That is our f of t. And we're going to end up with simply f of x, tangent of square root of tangent of x. That's the result. So they undo it. They're taking the derivative with respect to x of a differential that's going to be in terms of x, just gives you the function. And we also have another version of it, a chain rule version of it, where if we have a definite integral, let's say we have a definite integral from a constant a to a function of x, and we'll call it g of x, not just, once again, not to confuse our letters, of, come on, f of t dt, and we take the derivative with respect to x of this integral, we're going to get f of x, or let me say f, and instead of the t, like up here we plugged in the x, we're going to plug in whatever function of x is in here. So f of g of x times the derivative of whatever this function is. So let me give you an example of that. Let's say we have an integral of 2 to sine of x of x cube, t cubed dt. And we take the derivative of this with respect to x. We take the function. Here's our function again. This is our f of t. And we plug in, instead of t squared, it's going to be this function of x cubed. I should say cubed. So it's going to be sine of x cubed. So we plugged in this function into the t, where the t was, and then times the derivative of this function. So times cosine of x. I'd rather write that actually as in this way, sine cubed. That's the same thing, but there's your answer. These problems may look difficult, but if you see something like this that fits this fundamental theorem of calculus, you have an integral. Look for a constant as one bound of integration and a function of x as the other, and then we have a dummy variable, and you're taking the derivative. It's relatively simple. Play this over again if you're not sure. You're in the case with the x, you're just plugging in the x into this function, and you end up with in this case square root of tangent of x. You just take the function instead of the t, you get the x. Here, when it's a little bit more complicated and you have a function of x, you take that function, and instead of t, you plug in that function. Instead of t cubed, it's sine x cubed. And then you multiply it by the derivative of that function. It's that simple. There's certainly more of an explanation to this, but that's all I want to cover. You should be able to take the derivative of this kind of integral. So the other part, which I'm going to go into a little bit more depth, I'm going to show you a proof of this because this is very important, and we're going to be using it constantly. Is this right here? If we have an integral from a to b of f of x dx, and right now, instead of using the limit definition of the sum of n rectangles, we're going to say that this equals the antiderivative of the function f evaluated at b minus the antiderivative of this function evaluated at a, which is going to be quite a lot simpler than this up here, than our limit definition. And you remember how much time that can take and care it can take to write that out. So I'm going to give you a proof of this so we know how this works. So first of all, I have to give you a little bit of background, something that we didn't talk about yet. And this is going to be called the mean value theorem. Okay. So the mean value theorem basically says this: if we have a function on a closed interval a to b, let's say there's a function, it's a closed interval, it's continuous, and it's differentiable. We can take the derivative at any point in there, so there's no points there. It's all smooth. It says here that there's at least one point somewhere in here where the average rate of change from A to B is equal to the derivative at that point. So on the left here, we have the average rate of change, the difference in y over the difference in x. And what that gives us is, let me draw a picture, see if I can draw a line here. Okay. There is a line between here and here. So f of b minus f of a, the y values, divided by b minus a. Okay. And what this slope of this line, of course, we can see. We're looking at it visually. And there's at least one point somewhere in here where we have a point where the derivative is going to be equal to the slope of this line. So let's say right around here. Let's see if I can do this, right around there. And it looks like right around here. Yeah. So it looks like we have 2 points here in this function, right there. Yeah. Right, whatever point this is, let's say C1, and this point right here, which is I'm calling C2. So in this case, it's 2 points. So if we look at the average rate of change, that's represented by this line going from the beginning to the end points, the end point to the beginning point. And we see the slope there. Well, the tangent line at 2 places in this case is going to be the same slope as this slope. That's what this mean value theorem says. So knowing this, let's start with our proof of the fundamental theorem of calculus. So the first thing I'm going to do is we're going to talk about an interval from A to B. Okay? And we're going to split this interval up into n subintervals. Okay? So this one over here is going to be, we're going to call this point, the beginning point of A, x naught. That's a 0. And this last one is going to be x sub n. And then in between, we're going to have x1, x2, and so on, all the way up to x of n minus 2, x of n minus 1, all the way up to there, okay? So we're just labeling this way. It's convenient. You'll see why it helps. And so in this case, our A we can represent as x of 0 or x of naught, and B we can represent by x of n. And this entire interval can be split up in this way into n subintervals. The other thing we're going to say is that we're going to use the capital F of x is an antiderivative of little f of x. That means when you take the derivative of f of x, you get a big F of x, you get little f of x. That's what an antiderivative means. In other words, the derivative of this equals this. So the first thing I'm going to start with here is I'm going to write this. Capital F evaluated at B minus capital F evaluated at A. So the antiderivative evaluated at B minus the antiderivative evaluated at A. You can see why I want to do that, because we have this is our result here, that this integral, definite integral, equals exactly that. The antiderivative of whatever function is in here evaluated at one endpoint minus the evaluation at another endpoint. Okay, we're going to start there. And I'm going to say, because the way I can split up that interval above, I can say that this is the same thing as f evaluated at x of n, right? That's up here. This is b, right? B is x of n, minus the antiderivative evaluated at x of naught. Same thing. And then here's a kind of a tricky part. This, I am going to now use all these subintervals that we have in here. In other words, we're starting up here with, we have f of x of n. Well, the x of n is here. Well, the next one is down below it is x of n minus 1. And I'm going to talk about the interval here and say that this is equal to f of x of n minus f of x of n minus 1. I'm allowed to stick that in there as long as I add it again. Okay, so I have it, I'm subtracting it here and I'm adding it here. So together they cancel out and they're just 0. So I haven't really added anything. I haven't changed the value at all. I'm just changing the structure. And I'm going to keep doing that all the way down. The next one is going to be minus f of x of n minus 2. I'm going to carry over here, plus f of x of n minus 2. Okay, I'm subtracting and adding. So I added 0 here, I added 0 here, and I'm going to keep going on and on until I get to the other end of the interval here. I'm going down x2, x1 to x0. So the last interval, if you notice, is between from x0 to x1. And so I'm going to write f of x of 1 minus f of x of 0. Okay, so this is actually the same thing as the line above it. F of b minus f of a is the same thing as f of x of n minus f of x naught. We're just calling them those points different names. So instead of b, I'm calling it x of n. Instead of x of naught, I'm calling it a, or but the other way around. And then what I did is I started with that x of n minus 1. And at the end, we have x of x naught. And in between, I just added and subtracted over and over again, all of the all of the subintervals, and I didn't change the value at all because whatever I added, I subtracted. But we can now write it that way. So notice here then that this is the width of this last interval, right? F or the difference in the values of this last interval up here, x of n minus 1 to x of n. So that's the difference in the values between those two. And we keep going and going. This is the difference in values between the next two, and so on, all the way down to the last interval on the left. So let's look at one of these intervals. And now we have a whole bunch of these. We have n intervals represented here. And I'm just going to look at one subinterval. We're going to call it the ith interval. So that's like looking at a small part of the line. But we're going from this little point to this little point, a little subinterval. And so this is x of I, just some point in the middle, in between. It's not x of 1, it's not x of 13, it's just one of the x's in there. And the one over here, of course, would be then x of I minus 1. So the mean value theorem that we just talked about before says that let's look at it again. If f is continuous on a closed interval and differentiable on the open interval, then there's at least one point such that the mean difference equals the derivative of that point at that point. So let's take a look at that. So somewhere in here we have a point C. I'm going to call it C sub I. There's a point in there, and by the mean value theorem, I'll just write it like that. There exists, that's what that symbol means, there exists some point, C sub I, which is in the open interval, x of I minus 1 to x of I, okay? So it says just what we grew up here. There's a point, C sub I, somewhere in this interval in here, such that the derivative of that function at that point equals the mean value, x of I minus f evaluated at x of I minus 1 over x of I minus x of I minus 1. Okay, so that's the mean value theorem with respect to just one of these subintervals here. So if you notice here, this derivative on the left, the derivative, that's an antiderivative. So taking the derivative of that gives us the small function, the original function, f of C sub I. Okay? That's the relationship between an antiderivative and the derivative and the function. Okay? And so I'm just going to rewrite the right-hand side a little bit. The top I'm going to leave alone, f of x of I minus f of x of I minus 1. But if you notice in the denominator, x of I minus x of I minus 1 is, if at this little line, is the width of that interval, okay? The width of the subinterval. So I'm going to write delta x. That's what that means. That's the width of that subinterval. They're all in our what we're doing here, and you remember what we said that in this book and in our practice, we're just going to divide subintervals into even subintervals, so they're all the same. So we can just write it like that. So now I'm just going to do a little algebra. I'm going to multiply both sides of this equation by delta x. So I have over here f of C sub I times delta x equals f of x of I minus f of x of I minus 1. And I'm going to now take this equation here, and I'm just going to sum up from I equals 1 to n. So in other words, we're talking about the ith subinterval. This applies to every single interval that we divided this up into. Okay, so we're talking about with the ith interval, that just means one interval in here. Well, now this mean value theorem and this all what we wrote here applies to all of these subintervals. And so I can add them all up and say that the sum from I equals 1 to n of f of c sub I delta x equals the sum of I equals 1 to n of f of x of I minus f of x of I minus 1. And then I will call your attention to the fact that the right-hand side is exactly what we wrote up here with all these subintervals, writing out all these things, f of x of n minus f of x of n minus 1. We went all the way from x of n all the way down to x of naught and added them all together. These are all, each one of these pairs of differences here, we added them all together. That's what this says here. It says f of x of I, well, let's replace I with 1. So we have f of x of 1 minus f of x of 0. Okay, that would be our last one. Then we add the next one when f is 2, and it goes on, and we end up with this entire summation up here, which is actually the same thing as f of b minus f of a. So this summation here is just f of b minus f of a. If you're not sure about that, look at the notes, look at what this means, think about what this means, draw out a few terms and see that it looks exactly like what we had above. And so here we have, I'm just going to rewrite this side again. See in there. Okay. So the next thing I'm going to do is I'm going to take the limit as n goes to infinity of both sides here. So the limit as n goes to infinity of the left side, the sum from I equals 1 to n of f of c sub I delta x equals, I could write the limit, I'm going to take the limit as n goes to infinity, but these don't involve n at all. These are constants. So when we're talking about the limit as n does anything, and there's no n's, it's just going to be the same constant. So this remains the same. This here on the left should look familiar to you. The limit as n goes to infinity of the summation from I equals 1 to n of f of some point in each one of those intervals times delta x. That should look familiar because that is the definition, the limit definition of the integral from a to b of f of x dx. And the right-hand side is f of b minus f of a. And there is our proof of that. And this is actually one of the really brilliant parts of what makes up calculus, and the people that came up with this, Newton and Leibniz. This is a really brilliant bit of thinking, and this is going to come in very handy. And I'm going to give you a brief example. So let's say we have the integral from 1 to 2 of x squared. I'm going to make it a simple one. You should try all kinds of these integrals for practice, but we could use the limit definition and go through the whole process of taking the limit as x approaches infinity or n approaches infinity of the sum from I equals 1 and go through all that. But we now can use the fundamental theorem of calculus, which says if we can find the antiderivative of this function here, so this is our function, f of x. If we can find the antiderivative, and we know how to find the antiderivative of this is the power function, so we're going to say x cubed over 3. We are then going to evaluate that at the one endpoint, at the upper bound of integration minus the lower bound of integration. And I write that like this, 1 to 2. And that means that we're going to first evaluate and this is, let me write that this here is our antiderivative. So this is going to be 2. We're going to evaluate this at the upper bound of integration, so 2 cubed over 3. And then minus, we're going to now evaluate this function, this antiderivative, at the lower bound of integration, so 1 cubed over 3. So we have 8/3 minus 1/3 equals 7/3. There's your answer. So this one line here is certainly going to be a lot easier than using the limit definition. And that's the fundamental theorem of calculus. Go through all kinds of examples. Do your best to know that this works with just about every problem that we're going to use. On your exam, you're going to be asked once to use the limit definition, but the rest of the time, if you're not asked to use the limit definition, you can assume that you can use the fundamental theorem of calculus.